Alright, I'm going to be working a problem in the book today. Since we have an oxygen nucleus of 13 femtometers, that's just 1 meter times 10 to the negative 15. And we have a proton, it's heading towards it, and it says we're trying to find the velocity that would take for this thing to stop 1 femtometer away. So I have the solution worked out over here. First, just a picture to help you get a better understanding. Here's the proton. It's traveling this way, and the problem uses, it says it needs to be 1 femtometer away, and you need to have a little bit of intuition about what's going on. When you do the equations, you can't just set it to 1 femtometer. You would have to know that when you do a potential, the distance when you do a potential for radius is calculated from the center. So we have 1 femtometer, and then the radius of the nucleus is 3. So when we do the calculations, we're going to have to add them together, which is going to equal 4 for it to stop 1 meter or 1 femtometer outside the nucleus. And that's what it's asking in the problem. Alright, here's your typical setup. Energy is conserved, that's before, and that's the after. And again, I just set up with more variables and expanded it out. And you see right here, I just left this to fill in for the 1 femtometer later on. Alright, after canceling out some values, we have v squared is equal to this expression. And then once you do the square root, mathematically you're going to have a plus or minus, but it doesn't matter in this case. We're just looking for magnitude because we know it's heading towards the oxygen atom. Okay, and it was a normal neutral oxygen atom. So for the charge, we're only going to take into account the positive charges in here because with this problem, the electrons don't really give much of a effect because they're spread out and they don't make contact all at once. So they're only coming in contact with just a few at a time as they go, and also because they're spread out, a lot of the charges cancel out. So we have that's the fundamental charge in Coulomb for the 8 protons, the 1 proton. That's the K value. Here's the mass of the proton traveling. We're not going to consider the mass of the oxygen because we consider a lot larger. We consider it to not move as much. So it's negligible in this case. And here again, what I was mentioning earlier is the radius. We're including the whole radius of 4 femtometers. That's the 3 of the radius plus the 1 femtometer outside the shell of the radius. From here we just plug everything in. We have this number right here, it's just K, which is 9 times 9 to the 10. And we get this expression right here. And here's your final answer, right? It's 2.3 times 10 to the 7 roughly. And then the question also asks, what is the kinetic energy in electron volts? So we got to figure this in joules. So here's your velocity. Here's your typical kinetic energy equation. 1/2 mass velocity squared, which you just figured out, equals this expression right here. And then instead of writing it again, since it's so long, I just put it right here for that value. And then when I do the unit conversion right here, and it comes out to 2.88 mega electron volts. And you see, this is problem 43. That's what we get in the book.